Hello class, in this video I want to show you how you can perform a Z procedure for constructing a confidence interval for a proportion. So let's go ahead and read this problem. It says, suppose a chocolate factory is curious to see if using robots to assemble boxes of chocolates is feasible. The factory decides to use a set of robotic arms to select chocolate pieces from a conveyor belt and assemble them in a box. After a period of productivity, 500 boxes are randomly sampled and examined for defectiveness. So in this case, defectiveness means that the box is missing chocolates, or perhaps the chocolates have been placed in the wrong places. And so of the 500 samples, 17 were then defective. We want to calculate the 95% confidence interval to estimate the true proportion of defective boxes when the robot arms are used. So we are looking at, if we want to then kind of underline the important pieces, we have N is our sample size of 500. We have a random sample, that's important for our conditions. We're talking about a categorical variable, so using a proportion procedure is important here, and so we will use a Z procedure for proportions. X, the number of successes in our sample, was 17. That is, and it doesn't make sense that a defective piece would be successful, but success just essentially means the thing that we are going to be looking at, so the characteristic we are looking for. And the last couple things that we need is we want to do a 95% CI. Okay, so first, before we do any sort of calculations, let's talk about some conditions that need to be met. Well, first of all, we're talking about a proportion. So we want to estimate P, the true population proportion of defective boxes when robots are being used. And so this is our parameter that we are trying to estimate. And to do this type of procedure, we're going to use a Z procedure. So the formula is P hat plus or minus a Z critical value times then the standard error of our estimate, which in this case is P hat times 1 minus P hat all over N, the sample size. So before we can calculate this, we should check some conditions. First of all, to make inference, we always need a random sample. And in this case, we see up here that for sure that the sample was random. So this is met. And then another condition we should check is whether or not N times P hat is greater than 10 and N times 1 minus P hat is greater than 10. So before we do these calculations, let's go ahead and calculate P hat really quickly. P hat is simply just X, the number of successes, over the total sample size, and that is 17 out of 500 that are defective, and that comes out to be 0.034. So that's our proportion. So if we multiply 500 times 0.34, then it should be, and sorry, this is 0. Let's go ahead and erase that really quick. 0.034. We multiply 500 times 0.034, our P hat, then it should be no surprise that this is equal to 17, and that is of course greater than 10, so that condition is met. N times 1 minus P hat would be 500 times 0.966, which is equal to 483, which is again of course larger than 10. So both of these conditions are met. So we have our sample size conditions met, and we see that we have a random sample, so we can go forward and calculate from this formula. So from this formula, we start out with P hat plus or minus a Z critical value times then our standard error of P hat times 1 minus P hat all over N. If we go ahead and plug in these values, then again we get our point estimate to be 0.034 plus or minus a critical value of 1.96. That is because we're doing a 95% confidence interval, and so that goes along with a z critical value of 95%, times then our standard error, or standard deviation of the estimate, which is going to be the square root of 0.034, times then 1 minus this, which is 0.966, all divided by my sample size of 500. So here this comes out to be 0.034 plus or minus 1.96. This equation here comes out to be our standard error. If we multiply this out, comes out to be a value of 0.00814. And so if we multiply these two values together, let's make a little bit more room here. So if we multiply these two values together, this is called the margin of error. So this is the margin of error. It's our critical value times the standard error. This value comes out to be a positive 0.01589. And so this is the stuff that we add and subtract from then our point estimate. So this is our margin of error for a proportions problem. We have 0.034 plus this, 0.034 minus this, and we get a 95% CI then of 0.01811 and an upper bound of 0.04989. So if we want to make a conclusion, we can come down here to this conclusion and just simply state that the 95% confidence interval estimates the true proportion of defective chocolate boxes when robot arms are used is from, if you want to here then round a little bit, it's okay. I'm going to do that from 0.02 to 0.05 with a point estimate of 0.034. So you can round this however you want. I've just decided to round it this way. And this is how then we can write up a confidence interval for a proportion.